Good afternoon, everybody. Class begins. Last time we have talked about the performance of the CSMA protocol. Like this figure 4 shows the computed throughput or the performance with offered traffic for all three protocols: pure aloha, slotted aloha, and persistent with different algorithm, with different arguments. Then we have talked about CSMA with cognition detection. With cognition detection means stations can detect the cognition and abruptly stop transmitting when cognition occurs, rather than finish them, since they are irretrievably garbled anyway. It can save time and bandwidth. CSMA-CD is the basis of the classic Ethernet local area network. Station's hardware can listen to the channel while it is transmitting. That means a station can hear or sense the channel while transmitting. So if the signal it reads back is different from the signal it is putting out, then knows that a cognition is occurring. So it's stopped immediately. The implications are that a received signal must not be tiny compared to the transmitted signal, which is difficult for wireless, or as received signal may be 1,000,000 times weaker than transmitted signal. So it is difficult for wireless networks, and that modulation must be chosen to allow cognitions to be detected. And unfortunately, a cognition with two zero-voltage signals may well be impossible to detect. So this function of cognition detection has some limitation. With this figure, we can analyze the performance of CSMA-CD. For example, this we can depart the figures into different terms. We denote this point by T0, that is the beginning of a new term. Then after a contention period, and a frame can be successfully transmitted. Then next term, like before, with contention loss, with a successful frame transmission. So CSMA-CD can be divided into these stages: contention, transmission, or idle state. So at the point marked T0, a station has finished transmitting its frame. Any other station having a frame to send may now attempt to do so. If two or more stations decide to transmit simultaneously, there will be a cognition. If a station detects a cognition, it aborts its transmission. waits a random period of time and then tries again. Why it waits a random period of time? It can avoid the conditions occurs again and again. So a random period of time is adopted. Therefore, the model for CSMACD will consist of alternating contention and transmission periods, with idle periods occurring when all stations are quiet. Now, let's look at the details of the contention algorithm. Suppose that two stations both begin transmitting at exactly time t0. Then how long will it take them to realize that they have glided? The answer is vital to determine the length of the contention period and hence what the delay and the throughput will be. So the contention period, the length of the contention period is important to the analysis of the performance. Consider the following worst case scenario. Usually, we analyze the worst case scenario. It makes the basis of the performance network. Let the time for the signal to propagate between the two farthest stations be tau. At t0, the beginning of a new term, one station begins transmitting. At t0 plus tau minus a very small value, epsilon. Epsilon is but larger than 0, and very small. So at t0 plus tau minus epsilon, an instant. That means just at the point, an instant before the signal arrives at the most distant station. Since t0 plus tau, the signal definitely arrive at the most distant station. But minus epsilon, that means before the signal arrives at the most distant station, that station also begins transmitting. Why? Because the signal does not arrive at the most distant station. So the most distant station sends an idle channel, not a busy channel. So the station also begins transmitting. Of course, it detects the condition almost instantly and stops. But the constitution, the scenario does exist. But the little noise burst caused by the condition does not get back to the original station until time 2 times tau minus epsilon. So for the most distant station, it can almost instantly and stopped. But for the source station, it must it must sense the condition until when the noise signal get back to the original station. So it is 2 tau minus epsilon. In other words, in most cases, a station cannot be sure that it has seized the channel until it has transmitted for 2 tau. without hearing a condition. If a station hear a condition within 2 times tau, that the station will stop transmitting. So the worst case, a station cannot be sure within 2 tau. But if there is no condition within 2 tau time, the station will be sure that it can continue to finish the transmitting without condition any longer. So within 2 tau, it cannot be sure it has seized the channel. But after 2 tau, without hearing condition, it does be sure it has seized the channel, and it can continue finishing the remain frame. That is, this is the very important for analyze the performance. With this understanding, we can think of CSMA CD contention as a snorted aloha system with a snort width of 2 tau. For example, on the 1 kilometer long coaxial cable, tau is approximately equal to 5 milliseconds. The difference for CSMA CD compared to snort aloha is that snorts, in which only one station transmits, are followed by the rest of a frame. The difference will greatly improve performance if the frame time is much longer than the propagation time. That means the transmitting time is much longer than the propagation time. The channel will be almost busy the whole time. Although condition does occur with CSMA CD once a station has ambiguously captured the channel, they can still occur during the contention period. It means that although we have carrier sense or sense the channel before transmitting, but when a station is transmitting, other stations probably is also transmitting. It cannot avoid condition. It cannot completely avoid the condition. So these conditions adversely affect the system performance, especially when the bandwidth delay product is large. Bandwidth delay product is large means that the capacity, the number of frames in the network may be very large. So many frames can be transmitted in the network, such as when the cable is long and the frame are short. So the number of frames probably is very large. Not only do conditions reduce bandwidth, but they make the time to send a frame variable, which is not a good fit for real-time traffic, such as voice over IP or video streaming. So CSMACD is also not universally applicable for any application. Some protocols can be designed without conditions, such as condition-free. It depends on a basic bitmap method. For example, before a frame successfully transmitted, there is also a contention source. But the contention source is a bitmap. Any stations want to is ready for transmitting a frame. It denotes 1 bit, set 1 bit in the contention source. Then it can send its frame after contention source. For example, here station 137 has set 1 bit 1 in the contention source. So these 3 stations can transmit the frame 137. So after the last ready station has transmitted its frame, the event all stations can easily monitor. Another n-bit contention is begun. So the turn, the first turn, the second turn, the third turn. Then we have talked about token passing. Token passing, it passes a small message called a token from one station to the next in the same predefined order. The token represents permission to send. If a station has a frame queued for transmission, when it receives the token, it can send that frame before it passes the token to the next station. If it has no queue frame, it simply passes the token. So the token means the right to use the channel. In the token ring protocol, the topology of the network is used to define the order in which station sends. The stations are connected one to the next in the single ring. Passing the token to the next station then simply consists of receiving the token in or from one direction. Receive the token in from one direction and transmitting it out in the other direction. Figure 7 shows a typical token ring. Transmission direction is like this, and the token if a station grasps a token, then it means it can transmit its frame. Then we talked about the token bus. A token bus is a logical bus. Each station then uses the bus to send the token to the next in the predefined sequence. The predefined sequence is a logical concept. The positions of the token allows a station to use the bus to send one frame as before. This protocol is called token bus. Token rings have cropped up as MAC protocols with some consistency early token RAN protocol called token RAN, standardized as IEEE 802.5. It was popular in the 1980s as an alternative to classic Ethernet, but now it is a history since. In 1990, a much faster token RAN called FDDI, means Fiber Distributed Data Interface, was beaten out by switched Ethernet. So now, switched Ethernet is widely used nowadays. Binary countdown we will not talk in details. Now we will talk about wireless LAN protocols. Wireless LAN protocols are widely used nowadays because wireless network without coaxial or optical fibers, it is very convenient for mobile applications. A system of laptop computers that communicate by radio can be regarded as a wireless local area network, wireless LAN, usually standardized as IEEE 802.11. Such a local area network is an example of a broadcast channel. So wireless channel usually is a broadcast channel. It also has somewhat different properties than a wired local area network, which needs two different MAC protocols. Since the properties of the physical channel is different, one is wired, another is wireless, so the MAC protocols should be different because of different properties of the channel. A common configuration for a wireless local area network is an office building with access points strategically placed around the building. Access points is a very small devices was widely placed in the campus or in the factory. The access points are wired together using copper or fibers to provide connectivity to the stations that talk to them. So access points are connected with each other using wired lines. But laptops, smartphones, or any other wireless ends can contact with access points with wireless channel with air interface. If the transmission power of access points and laptops is adjusted to have a range of tens of meters, usually 50 meters, the range of 50 meters, nearby rooms becomes like a single cell, and the entire building becomes like the cellular telephone system, except that each cell only has one channel. This channel is shared by all stations in the cell, including the access points, AP. It typically provides megabits per second bandwidth up to hundreds of megabits per second. This number will be higher and higher because the performance of this wireless lens will be improved rapidly. Wireless systems cannot normally detect a condition while it is occurring. The received signal at a station may be tiny, perhaps 1,000,000 times fainter than the signal that it is being transmitted. So the signal received may be tiny, millions times fainter than the original signal. Instead, acknowledgements are used to discover conditions and other errors after the fact. A station on the wireless local area network may not be able to transmit frames to or receive frames from all other stations because of limited radio range of the station. In wired lens, when one station sends a frame, all other stations receive it, right? Because they are in the same, connected to the same bus, connected to the same wired channel, a broadcast media. The absence of this property in wireless lens causes a variety of complications. So these properties does not exist in wireless local area network. It makes some complication problems in wireless environment. We will make a simplified assumption that each radio transmitter has some fixed range represented by a circular coverage region within which another station can sense and receive station's transmission. It is important to realize that, in practice, coverage regions are not nearly so regular because the propagation of radio signals depends on the environment. For example, obstacles, for example, the walls or any other, or trees, houses, etc. So walls and other obstacles that attenuate and reflect the signals may cause the range to differ markedly in different directions. It is not a regular circular coverage region, but a simple circular model will do for our purpose. If we assume a regular simple circular model, it will be very easy for us to analyze the problem. With what matters for reception is interference at the receiver, not at the sender. So the interference only exists at the receiver. If two ways of signal arrive at the same receiver, then conditions will occur at the receiver, but not at the sender. To see the nature of the problem, consider Figure 11, where 4 wireless stations are illustrated. For our purposes, it does not matter which are AG and which are laptops or any other wireless machines. The radio range is such that A and B are within each other's range example, if the radius of the communication is the distance from A to B, so the radio range A is within the radio range of B, and B is within the radio range of A. They can be reach each other. Then can potentially A and B are within each other's range, and they can potentially interfere with one another. So the advantage is A and B can reach with each other, but they can also interfere with one another. The disadvantage is they interfere with one another. So they can communicate with each other and they interfere with each other. So then we consider the third laptops or APs. C can also potentially interfere with B and D. You can look at the subfigure A, B, C, and D. So C is within the radio range of B and D. B is within the radio range of A and C. A is within the range of B. D is within the range of C. So C is out of the range of A. A is out of the range of C. D is out of the range of B. B is out of range of D. So we set such scenarios for analyze some special problems, hidden terminals or exposed terminals problems. Subfigure A shows hidden terminal problems. A and C are hidden terminals when transmitting to B. And B and C are exposed terminals when transmitting to A and D respectively. Now we will analyze the problems, how the problems affect the performance. First, consider what happens when A and C transmit to B, as depicted in subfigure A. If A sends and then C immediately sends the media, it will not hear A because A is out of the range of C, right? Thus, C will falsely conclude that it can transmit to B. If C does start transmitting, it will interfere at B. So B is a receiver. Then signals from A and another signal from C arrive at the B at the same time. So collision occurs at the receiver B. So it will interfere at B, wiping out the frame from A. We assume here that no CDMA type scams is used to provide multiple channels, so collisions gobble the signal and destroy both frames. That is what the collision affect the transmission. The two frames from A and C both are destroyed. So we want a map protocol that will prevent this kind of collision from happening, because the collision with the bandwidth, right? So we should make a new MAC protocols prevent this kind of condition from happening. The problem of a station not being able to detect a potential competitor for the media because the competitor is too far away. So this problem is called hidden terminal problem. This is the first famous problem in the wireless local area network. A different situation is B transmitting to A at the same time. Based on subfig B, B transmitting to A is here, B is transmitting to A, and C is transmitting to D. Right? We should, the analysis now based on subfig B. B transmitting to A to the left, right? C wants to transmit to D to the right direction. If C sends the media, it will hear a transmission and falsely conclude that it may not send to D. But in fact, such a transmission would cause bad reception only in the zone between B and C, where neither of the intended receivers is located. So, it does not interfere with one another. The B to A and C to D can be transmitted simultaneously without any interference at all. So we want a new MAC protocols that prevent this kind of deferral from happening, because it's with the bandwidth too, right? The first problem, hidden terminal problem, reduce the performance, and the second expose the terminal problems with the bandwidth too. So for the wireless local area network, we should design a special MAC protocols for the wireless environment. That is different from the properties of wired network. The difficulty is that before starting a transmission, a station really wants to know whether there is the radio activity around the receiver. But how can the sender know what will happen at the receiver? The sender does not know at all. It is difficult for the sender to know what will happen at the receiver point. CSMA merely tells it whether there is activity near the transmitter by sensing the carrier, right? So CSMA can merely tell it whether there is an activity near the sender, near the transmitter, but not near the receiver. We know the interference occurs at the receiver, but the CSMA does not let the transmitter know. In a system based on short-range radio waves, multiple transmissions can occur simultaneously if they all have different directions and these destinations are out of range of one another. So, a new MAC protocols which is different from wired local area network is invented, which tackles the two famous problems for wireless local area network. the basic idea behind it is for the sender to stimulate the receiver into outputting a short frame with a kind of control information. So stations nearby can detect this transmission and avoid transmitting for the duration of the upcoming data frame. This technique is used instead of carrier sense. So this is the basic idea of MACA, that is multiple access with collision avoidance, invented in 1990. This figure shows the principles of MACA collision. CA means collision avoidance, not collision detection. So detection can be done in wired network, but CA is designed for wireless network. This kind of short frame here, short frame is RTS and CTS. A sending an RTS to B. RTS means request to send. A sending a RTS to B, and B responding with a CTS to A. CTS means clear to send. So A starts by sending an RTS frame to B as shown subfigure A. This short frame, about 30 bytes, contains the names of the frame that will eventually follow. So what's the function of the short frames? It acts like some reservation of the resources for the station. It tells the other stations, I will use the channel with a short time, with a short period. So you should wait until I finish my transmission, right? So that is why the short frames are adopted. It contains the names of the data frame that will eventually follow. Then B replies with CTS, means clear to send. It's also a short frames. CTS frames contains the data names copied from the RTS frames. So the stations around near the station B will know B will be a receiver in the near times. Upon receipt of CTS frames, then A begins transmission. So RTS and CTS works as the resource reservation. Now let's see how stations overhearing either of these frames react. Any station hearing the RTS is close to A and must remain silent long enough for the CTS to be transmitted back to A without conflict. Any station hearing CTS is clearly close to B and must remain silent during the upcoming data transmission, whose length it can tell by examining the CTS frame. So the stations close to A and B will keep silent until A and B finish their transmissions, right? In Fig 12, this kind of figure, Fig 12, C is within the range of A, but not within the range of B. Therefore, it hears RTS from A, but not CTS from B. As long as it does not interfere with CTS, it is free to transmit while the data frame is being sent. In contrast, D is within range of B, but not within the range of A. It does not hear the RTS, but does hear the CTS. Hearing the CTS tips it off that it is close to a station that is about to receive a frame. So it differs and delays sending anything until that frame is expected to be finished. When will the frames will be finished transmission? How can the other stations know how long they should wait? Because the CTS and RTS contains the data length. So other stations can know how long they will wait for. Station E hears both control messages and, like D, must be silent until the data frame is complete, is transmitted successfully. Despite these precautions, collisions can still occur. So the collision cannot completely avoid. But these structures, these arrangements will avoid almost collisions, right? For example, B and C can both send RTS frames to A at the same time. This will collide and be lost. In the event of a collision, an inaccessible transmitter waits a random amount of time and tries again later. Then, just now we have talked about wireless MAC protocol. Now, we will talk about the MAC protocols designed for Ethernet. Is usually wired networks. How do these principles of channel allocation protocols apply to real systems? Many of the designs for personal, local, and metropolitan area network have been standardized under the name of IEEE 802. The most important of the survivals are 802.3 for Ethernet and .11 for wireless local area network. Bluetooth for wireless personal area network (PAN) is widely deployed, but has now been standardized out of .15, with .16 for wireless metropolitan area network. It is too early to tell. Okay, we will begin our study of real systems with Ethernet, probably the most ubiquitous kind of computer network in the world. Two kinds of Ethernet exist: classic Ethernet and switched Ethernet. Classic Ethernet, which solves the multiple access problem using the techniques we have studied in this chapter. And switched Ethernet uses switches called switches. Connect different computers. It is important to note that while they are both referred to as Ethernet, they are quite different. Classic Ethernet is the original form and ran at rates from 3 to 10 megabps. We know this data rate is considerably low. What switched Ethernet is what Ethernet has become and runs at 100, 1000, and 10,000 and even higher speed in forms called fast Ethernet, gigabit Ethernet, and 10 gigabit Ethernet, and this beyond this kind of speed. In practice, only switched Ethernet is used nowadays. So classic Ethernet has become historical since. Now, switched Ethernet is widely used. Ethernet and IEEE 802.3 are identical except for a minor difference. Many people use the terms Ethernet and .3 interchangeably, so they are almost the same concept. The history of Ethernet starts about the same time as that of Aloha, when a student named Bob Metcalfe got his bachelor's degree at MIT. So Metcalfe is the father of Ethernet. So this slide shows the stories of the Ethernet, how the Ethernet invented. Metcalfe then moved up to get his degree at Harvard. During his studies, he was exposed to this person's work group. He became so interested in the network that after graduating from Harvard, he decided to spend the summer in Hawaii working with Ramson before starting work at the Xerox PARC. PARC, P-A-R-C, means Palo Alto Research Center. It's a very famous research institution. When he got to PARC, he saw that researchers there have designed and built what would later be called personal computers. But the machines were isolated. They cannot communicate with each other. For example, people sharing files, sharing documents only by disks, soft disk, not network. So the machines were isolated that time. So using his knowledge of Emerson's work, he, together with his colleague, David Boggs, designed and implemented the first local area network in 1976. it used a single long, thick coaxial cable, and the speed is only 3 megabps. It is a great thing at that time because it is the first local area network, right? So although the data rate is very low, but it is the first local area network. They call the system Ethernet after the Ether concept. The Xerox Ethernet was so successful that these three companies, DEC, Intel, and Xerox, drew up a standard in 1978 for a 10 megabps Ethernet called the DIX standard with a minor change. The DIX, DEC, the first letter D, DEC, Intel, and Xerox. So the DIX standard became the IEEE 802.3 standard in 1983. When Xerox showed little interest in doing anything with Ethernet other than helping standardize it, Metcalfe formed his own company. 3Com. 3Com has been very famous many years ago. To sell Ethernet adapters for PC. So 3Com company sells network interface adapter for PCs. So with adapters, Ethernet adapters, then PCs can connect to the network, right? So it serves many millions of them. The classic Ethernet sneaked around the building as a single long cable to which all the computers were attached. So figure 13 shows this architecture. This is a long cable, single long cable. This is a PC, personal computer, connected to the cable with a network adapter. This is a network adapter, which is a transceiver. Transceiver means transmitter and receiver. Transmitter, and it is a unit of transmitter and the receiver. So you see interface cable. Interface. This is an interface cable connected to the PC. Why we say the Ethernet sneaked around the building? Because this is a long cable, can be around the desk in the room with different shapes. The first variety, popularly called thick Ethernet, resembled a yellow garden hose with markings every 2.5 meters to show where to attach computers. The other type is thin Ethernet, which bent more easily and made connections using industry standard BNC connector within thin Ethernet was much cheaper and easier to install, but it could run for only 185 meters per segment instead of 500 meters with thick Ethernet, each of which could handle only 30 machines instead of 100 machines. But thick Ethernet is more expensive than thick Ethernet. So thick Ethernet can be some more power with a higher performance than thin Ethernet. Each version of Ethernet has a maximum cable length per segment over which the signal will propagate. To allow larger networks, multiple cables can be connected by repeaters. A repeater is a physical layer devices that receives, amplifies, and retransmits signals in both directions. Over each of these cables, information was sent using the Manchester encoding. Is a kind of code method we have talked about in the formal sections. Ethernet could contain multiple cable segments and multiple repeaters, but no two transceivers could be more than 2.5 kilometers apart, and no path between any two transceivers, transmitter and receiver, could traverse more than 4 repeaters. Okay, this figure shows the format of the frame transmitted in the Ethernet. So the format used to send frames is shown. Look at the subfigure A and B. A is with Ethernet DRX. B is for IEEE 802.3. And in the subfigure A, there is 8 bytes for preamble bits, then followed by destination address of 6 bits, then 6 bytes, 6 bytes source address, 6 bytes destination address, 2 bytes type field, then a variable length of data payload, right? Then is a pad field if necessary, pad. The last field is checksum with 4 bytes. So what is the difference between A and B? What's the difference between Ethernet DRX and .3? Only 2 bytes. Only within only 2 bytes. For Ethernet DRX format, this 2 bytes is type field, is used for type. But in IEEE 802.3, this 2 byte is used for length. What kind of format is usually used in nowadays network. That is the Ethernet. That is the Ethernet. So type is usually in the nowadays local area network. Then this slide explains the formats of the frame. The first field is a preamble field, each containing a bit pattern 10101010, with the exception of the last byte, in which the last 2 bits are set to double 1 bit. This last byte is called the start of frame delimiter for .3. Matches the encoding of this pattern produces 10 MHz square waves for 6.4 milliseconds to allow the receiver's clock to synchronize with the sender's. The last 2 1 bits tells the receiver that the rest of the frame is about to start. So that is why the preamble is necessary. Next come 2 addresses, one for the destination and one for the source. They are each 6 bytes long. The first transmitted bit of the destination address is a 0 for ordinary addresses and a 1 for group addresses. Group addresses allow multiple stations to listen to a single addresses. Once a frame is sent to a group address, all the stations in the group received it. Sending to a group of stations is called multicasting. The special address consisting of all 1 bits is reserved for broadcasting. An interesting feature of station source addresses is that they are globally unique, assigned centrally by IEEE to ensure that no 2 stations anywhere in the world have the same address. No 2 stations have the same address. The idea is that any station can uniquely address any other stations by just giving the right 48-bit number. To do this, the first 3 bytes of the address field are used for OUI segment. OUI means organizationally unique identifier. Values for this field are assigned by IEEE and indicate a manufacturer. Manufacturers are assigned blocks of 2 with the power of 24 addresses. It is a very large number. A manufacturer assigns the last 3 bytes of the address and programs complete addresses into the NIC before it is sold. NIC means network interface card or network adapter. Network interface card, also called network adapter. So the format MAC frame format. Next comes the type of nonce field. This 2 bytes field is type or nonce depending on whether the frame is Ethernet or IEEE 802.3. Ethernet uses a type field to tell the receiver what to do with the frame. It is widely used nowadays. Multiple network layer protocols may be in use at the same time on the same machine. So when an Ethernet frame arrives, the operating system has to know which one to hand the frame to. The type field specifies which processes to give the frame to. For example, a type code 0800 means that the data contains an IPv4 packet. So the data in the frame will be delivered to the IPv4 for processing, right? On the other hand, IEEE 802.3 decided that this field would carry the length of the frame. It works for capacity. Header for LLC protocols within the data. It uses 8 bytes to convey the 2 bytes of protocol type information. Unfortunately, by the time .3 was published, so much hardware and software for DIX Ethernet was already in use that few manufacturers and users were enthusiastic about repackaging the type and length fields. So actually, this 2-byte field is used with type, not length field. Now the rule is that any number there less than or equal to 1536 can be is also hexadecimal 600 can be interpreted as length, and any number greater than this value can be interpreted as type. So it very perfect method to dealing with these different types. Next come the data up to the maximum length of the data is up to 1500 bytes. This limit has chosen somewhat arbitrarily at the time the Ethernet standard was cast in stone, mostly based on the fact that the transceiver needs enough random access memory to hold entire frame, and RAM was expensive in 1978. A larger upper limit would have meant more RAM, and hence more expensive transceivers. In addition to there being a maximum frame length, there is also a minimum frame length. To make it easier to distinguish valid frames from garbage, Ethernet requires that valid frames must be at least 64 bytes long. From destination address to checksums, including both. If the data portion of a frame is less than 46 bytes, the path field is used for filling out the frame to the minimum size. Another and more important reason for having a minimum length frame is to prevent a station from completing the transmission of a short frame before the first bit has been reached the far end of the cable, where it may collide with another frame. But the sender does not know. So this is the more important reason for having minimum length frame. That is used to prevent a station from completing the transmission before the first bit has even reached the far end of the cable, but with connection with other machines. This problem is illustrated in Figure 15. In 15, we assumed that condition detection can take as long as 2 tau. Tau, what is the concept of tau? Tau is the propagation delay from A to the farthest end on the cable. So it also considered as the propagation delay from A to D. So tau. Then the 2 tau means A to B and turn back to A. The round trip time. Okay, so much for today. Thank you. 小孩参加陪酒跳绳，没说过结婚，也没说过结婚，也没说过。参加陪酒跳绳，也没说过结果。继续做合作。